Yesterday we learned about how to do electron configurations, which, just to review, basically it shows the electron's address. It's the most probable location to find an electron. So today we're going to do the same thing, except we're going to add on if you're trying to do it for an ion. So let's review the word ion, because I know it's been a while since we did that. An ion is any particle that has a charge on it, which means it either gained or lost an electron. So if you're given an ion, first thing you want to do is go ahead and write the electron configuration for the neutral atom. Then you're going to add electrons if it's negative, or take them away if it's positive. And don't forget that it's opposite of what you think. Negative tends to make you think take away, so make sure you remember it's opposite. And you always want to remove electrons from the highest orbital or the biggest coefficient first. So for example, if I said to write the electron configuration for sulfur 2-, the first thing you want to do is just write the configuration for sulfur without the 2-. So if you look at the periodic table, sulfur is kind of towards the top right corner. So you'd go up a row all the way over to neon and put it in brackets, and then you'd have 3s2 and 3p4. I didn't abbreviate mine, but it's the same thing except yours is abbreviated. The second thing you want to do is look at the charge and decide if you're gaining or losing electrons. So a -2 means that you need to add 2 more electrons into the configuration. Well, the 3p4 could still fit some more in there, because if you remember from before, the p can hold up to 6 electrons, the p orbital. So what we're going to do is add 2 more, and now it becomes 3p6. And that's the only difference. So here's a few examples. Go ahead and pause this and see if you can do these examples on your own. Once you've tried all 4, I want you to check your answers and notice that you probably did okay with the first 2. I want you to see that they both filled up the p orbital completely, and you'll find that to be very common because elements are extremely stable when they have full orbitals. So they're going to tend to gain or lose electrons to make them become full. Notice that for nickel, you may have had something different. If your answer said 4s2 3d7, that's a very common mistake. So when you're taking away electrons, it's tempting to always take them away from the last one that you wrote, but you want to make sure you take it away from the largest coefficient. So since 4 is bigger than 3, you're going to take it away from the 4s2 instead of the 3d8. So always look for the biggest coefficient and remove them from that orbital. Orbital notation is similar to electron configuration, except you're using arrows to show the electrons. So if you notice for sulfur, the electron configuration is 3s2, 3p4. For an s, we talked about a long time ago that s only has 1 orbital, which means it can only be turned one way. P has 3, D has 5, and F has 7. Make a little note on your notes right where you're writing right now and just write S1, P3, D5, and F7. That's how many boxes you're going to draw for the orbital notation. So every time you have an S, you're going to draw 1 box, and the little number right up here, this little thing that looks like an exponent, tells you how many arrows to draw in that box. So this represents the number of electrons, and now you're going to put the electrons in the box. However, there's a couple of rules to remember. We talked about these a couple days ago. The opposite spins rule is Pauli's exclusion principle, and it says that if you have 2 electrons in the same orbital right here, they have to be going opposite directions. So it would be incorrect to have 2 arrows both pointing up or 2 arrows both pointing down in the same box. Excuse me. The second rule is the fair share rule, and this one says that this is Hund's rule. If you have a set of boxes, like the P has 3 sets of boxes, when you're putting your arrows in, you need to spread them out as much as possible. So if you have 4 arrows, you're going to put 1 in each box before you come back for seconds. Here's a few examples. The first thing you'll want to do is write the abbreviated electron configuration, and then you want to draw the orbital notations. So again, go ahead and pause this video and try them yourselves, and then I'll talk you through it and we'll see if you got the same thing I did. So for silicon, you should have gotten the abbreviated configuration is neon in brackets, 3s2, 3p2. So when you draw your arrows, you should have one box for the 3s with 2 arrows, one up and one down. For P, you should have 3 boxes, but since you only have 2 arrows, you should spread them out, so 1 arrow in 2 of the boxes, and then one of the boxes will just be blank. For arsenic, here's your electron configuration. You should have 1 box for the S with an up-down arrow, two arrows, one up and one down. For the D, you should have 5 boxes, and every box should have an up arrow and a down arrow. And then for the P, you should have 3 boxes, and all 3 should have 1 arrow pointing up. And the last one is strontium. You should just have 1 box with 2 arrows, 1 up and 1 down. The last thing for today is actually an extremely important new vocabulary word, and that is valence electrons. Valence electrons are the ones that are in the outermost energy level. And the key word there is outermost, so you want to make sure you highlight that word or put a star by it or circle it in your notes. When you see valence, you need to think outer shell, or the outermost energy level. And really, those are the only electrons we care about. So the electrons that are stuck in the middle of the atom, right next to the nucleus, they're not going to be traded or shared or borrowed or stolen, so they're not going to react, and we don't really care about them. They're just going to kind of sit there. It's the ones on the outside that are going to be traded and moved around to different elements, which is going to cause chemical reactions. So that's why we care about those. It's important because it determines the physical and chemical properties of the elements. So for example, all the elements that have 1 valence electron, they all react almost exactly the same way. All the elements that have 7 valence electrons, they're going to react the same way. So the number of valence electrons determines the properties of the elements. That's really important. Put a star by that. And you can use the periodic table to figure out how many valence electrons there are. So if you have your periodic table out, I'm going to tell you to label some things, and if not, go ahead and pause the video and grab your periodic table. And what you want to do is label across the top. So find hydrogen at the very top left corner and put a 1 on top of it. Every element in that column underneath hydrogen has 1 valence electron. Then go to beryllium and put a 2 on top of beryllium. Everything under beryllium has 2 valence electrons. Skip over the entire D block. So the middle of the periodic table, just skip over it until you get to the P block, letter B for boron. And on top of boron, put a 3. On top of carbon, put a 4. On top of nitrogen, 5. Oxygen, 6. Fluorine, 7. And helium, 8. So that's how many valence electrons that you have for each of those elements. All you have to do is look at the top and see how many you have. There is an exception though. Helium only has 2 valence electrons because it's in that first energy level that only has an s orbital. So it can only have 2. So next to helium, just make a little note that it has 2 valence electrons, even though everything underneath it, so neon, argon, krypton, all of those have 8. And for now, the D and the F block elements, you can assume they have 2 valence electrons. So where you wrote the letter D, just put in parentheses, assume 2 valence electrons. Same thing for F, you can put in parentheses, assume 2 valence electrons. So pause this real quick and see if you can find these elements and tell me how many valence electrons they have, and then check your answers. Silicon, you should have 4. Bromine is 7. Aluminum is 3. Antimony is 5. And cesium is 1. And that's the last lesson for this chapter, so you now have all the information for the atomic theory test.